Welcome to Lecture 10, Section 3.3, the Intermediate Value Theorem. Once more, we are using the text Advanced Calculus by Patrick M. Fitzpatrick, and this is Dr. Gilbert Iyabi. Section 3.3, the Intermediate Value Theorem. The second important geometric property of the graph of a continuous function that we will establish is that if a continuous function has a domain consisting of an interval, and if its graph contains points that are both above and below the line y equals c, then in fact we would conclude that the graph intersects the line y equals c. Now let's put that more rigorously. Subsection 3.3.1, the IVT. Suppose f is a function that is continuous on the closed bounded interval. Let c be a real number. C is strictly between f of a and f of b. That means we could have f of a less than c less than f of b, or f of b less than c less than f of a. If this is the case, then we conclude that there is a number x naught in the open interval AB such that f of x naught equals c. Now let's look at the geometric picture of what we have just explained before we can look at the proof of IVT. So here is the first scenario. A, B. F is continuous on the closed bounded interval AB. Here is our f of A and here is our f of B. Now f of a and f of b are function values because f is continuous at the endpoints. Observe here that f of a is less than c, which is less than f of b. This line is the line y equals c. So IVT says if f is continuous on this closed bounded interval and there is a c between f of a and f of b strictly, then I can always find an x naught such that f of x naught equals c. In other words, the graph of this continuous function intersects the line y equals c. As a matter of fact, for this particular case, you can see that we have a point right here, which is a point of intersection. Here is another point, and here is another point. Now, let's look at the second scenario. Here we have f of b less than c, which is less than f of a. Again, we can always find an x naught between a and b such that f of x naught equals c. Or we can say such that the graph of the continuous function on the closed bounded interval AB intersects the line y equals c. Now that we have the geometric pictures, I want us to go ahead and give you the proof of the intermediate value theorem, and we shall use the bisection method. Proof. We shall use the bisection method, and we would consider the case f of a less than c and f of b greater than c. In other words, we'll look at the case f of a less than c, which is also less than f of b, and all the inequalities are strict. What about the other case? Well, the other case follows from this by replacing f by negative f and c by negative c. Now, the strategy we would use will be to recursively define a sequence of nested closed subintervals of our closed bounded interval AB, whose endpoints would converge to a point in the closed bounded interval AB at which f of x equals c. Sounds complex, but not as bad as it sounds. Let's go ahead and do that. Now, let us set A1 to be the lower endpoint A and B1 to be the upper endpoint B. Now, let n be a natural number. Suppose that the interval a and bn, closed bounded interval a and bn contained in AB has been defined such that f of an is less than or equal to c and f of bn is strictly greater than c. Let us go ahead and define the midpoint of our interval a and bn as an plus bn divided by 2. We have a couple of cases here. Number one, if f of the midpoint is less than or equal to c, then go ahead and define an plus 1 to be the midpoint mn and bn plus 1 to be bn. If f of the midpoint mn is strictly greater than c, then go ahead and define an plus 1 and bn plus 1 as the midpoint mn. Let's geometrically explain that. So here we are, the first case. F of mn is less than or equal to c. If that happens, then define an plus 1 to be mn and bn plus 1 to be bn. And you can see from this diagram that there will be some point x0 at which f of x0 equals c, where f intersects the line y equals c. And in the second case, if f of the midpoint is strictly greater than c, then we're going to define an to be an plus 1 and bn plus 1 to be the midpoint mn, in which case you can still see that there is going to be some x0 here such that f of x0 would be c. In other words, f intersects the line y equals c at the point x0. Now let's go ahead and complete the proof. Now I want you to observe from what we have done so far that for every natural number n, the following chain of inequalities will hold, i.e. a is less than or equal to an, which is less than or equal to an plus 1, which is strictly less than bn plus 1, and that is less than or equal to bn, which is less than or equal to b, number 1. Number 2, f of an plus 1 is less than or equal to c from how we define our function f, and f of bn plus 1 is strictly greater than c. And thirdly, bn plus 1 minus an plus 1 equals bn minus an, all of that divided by 2. Therefore, it follows that bn minus an equals b minus a divided by 2 for every natural number n. Thus, the sequences an and bn satisfy the assumptions of the nested interval theorem. Again, if you have forgotten the assumptions of the nested interval theorem, I'll refer you back to sections 3.1 and 3.2. Therefore, we can conclude that there exists a real number x0 in AB such that the sequence an converges to x0 and the sequence bn converges to x0. But wait a minute. F is continuous on the closed bounded interval AB. x0 is from AB. Therefore, F is continuous at the point x0. And by the sequential definition of continuity, we can say that f of an converges to f of x0 and f of bn converges to f of x0. Conclusion: it follows that f of x0 is less than or equal to c, since f of an is less than or equal to c for every natural number n, and that f of x0 is greater than or equal to c, since f of bn is greater than or equal to c for every natural number n. Consequently, we can conclude that f of x0 equals c, and that brings us to the end of the proof. Now, the proof is probably a little challenging and not exactly like some of the proofs we've seen before, but just go through it a couple of times and you should be able to follow it. But what I want to say to us here is that I expect you to remember the wordings of the theorem. If I define a continuous function on a closed bounded interval AB, and there is a point C that is strictly between f of A and f of B, then there exists a real number x0 in the open interval AB such that f of x0 equals C. And let's go ahead and look at a few application problems so that the concept of IVT can sink in. First application, example 1. Use the intermediate value theorem to show that for every positive real number C, there exists a solution to the equation x squared equals c. X is strictly greater than 0. All I have to do here is define a continuous function f on a closed bounded interval In this case, our f of x is x squared. So why don't I define my a to be 0 and my b to be c plus 1? Then f is a continuous function on the closed bounded interval 0, c plus 1. Why is f continuous? Well, f is a polynomial function, and as I mentioned before, back in chapter 2, polynomial functions are continuous on the entire set of real numbers. So f is a continuous function on this closed bounded interval. Now go ahead and evaluate f of 0. You'd get 0, which is less than c because c is positive. Also, f of c plus 1 will give you c squared plus 2c plus 1. We are adding positive terms, plus 1, so that is definitely greater than c. So we have that f of 0 is less than c, which is less than f of c plus 1. Therefore, by the intermediate value theorem, I can conclude that there exists a real number x naught in the open interval 0, c plus 1 such that f of x naught equals c, i.e. x naught squared equals c. X naught is a solution of our equation. In other words, whenever we have the equation x squared equals c, I can always find a solution to that equation, and my solution is x naught. Now, recall that this is not a constructive proof. This is a non-constructive proof. Finding the particular x naught is a whole different question. In this proof, we have simply established the existence of such a solution, but we haven't found the solution itself. Example 2. Prove that the following equation x to the 5 plus x plus 1 equals 0 has a solution where x is a real number. Again, just like example 1, we want to define a continuous function on some closed bounded interval and conclude that there exists an x naught in the open interval AB such that h of x naught equals what we're interested in. In this case, it will be 0. So let's go ahead and show you how that is done. Define the function h from the set of real numbers to the set of real numbers by h of x equals x to the 5 plus x plus 1 for every real number x. Then h is continuous as a polynomial function. Now observe that h of negative 2 is less than 0 and h of 0 is greater than 0. So 0 is strictly between h of negative 2 and h of 0. Therefore, by the intermediate value theorem, if I restrict my h from the closed bounded interval negative 2, 0 to r, then there exists an x naught in the open interval negative 2, 0 such that x naught is a solution to my equation x to the 5 plus x plus 1 equals 0. Again, I have without any doubt shown that the equation x to the 5 plus x plus 1 has a solution. I did not provide any solution, but without any reasonable doubt, a solution does exist. Finding the solution is a whole different question, which is not handled under the intermediate value theorem. Now, what I expect you to do is write out the expanded proof. So I need you to find h of 0, h of negative 2, and actually show that h of negative 2 is less than 0, which is less than h of 0, and then see why we had the right to apply the intermediate value theorem in this case. Before we leave section 3.3, I want to introduce you to what is known as a convex set. Let D be a subset of the set of real numbers R. Then we say that D is convex if whenever U and V are elements in D where U is less than V, then the closed bounded interval UV is contained in D. So let's look at this picture right here. Let's say this is our set D. U and V are elements in the set D such that U is less than V. If there are some values between U and V that are outside of this set, then D is not a convex set. D is convex if the closed bounded interval, all the values between U and V with U and V included, all those values are elements in D. The entire interval is a subset of the set D. Okay, let's go ahead and use that definition to prove the second theorem in section 3.3. Subsection 3.3.3 theorem. Let I be an interval, and suppose that the function f from I to R is continuous. Then we conclude that its image f of I is also an interval. Now I want you to watch the statement of this theorem very carefully. Number one, I has to be an interval. Number two, f is a function from I to R. Number three, f is continuous. If these three properties hold, then we can conclude that the image set f of I is also an interval. Let's go ahead and prove that, and we would come to the end of section 3.3. We show that the image f of I is a convex set. Let y1 and y2 be elements of the image f of I, where y1 is less than y2. Our goal is to prove that the closed bounded interval y1, y2 is a subset of the image set f of I. Indeed, let y1 be less than some real number c, which is less than y2, and the inequalities here are strict. Since y1 and y2 are in the image set f of I, there are points x1, x2 in I where f of x1 equals y1 and f of x2 equals y2. That is simply the definition of the image of a function. If we let J to be the closed interval having x1 and x2 as endpoints, then J is contained in I, since by assumption the set I is an interval and therefore it is convex. Thus, we can apply the intermediate value theorem to the function f from J to R in order to conclude that there exists an x0 in J at which f of x0 equals c. Thus, x0 belongs to I and f of x0 equals c. It follows that the closed bounded interval y1, y2 is contained in the image set f of I. We have thus proved that the image set f of I is convex. In other words, if you pick any two elements in f of I, with one element being less than the other, then the closed bounded interval between those two elements is a subset of f of I, and that brings us to the end of the proof of theorem 3.3.3, and it also brings us to the end of section 3.3, the intermediate value theorem. And I'll see you next with section 3.4, where we start looking at the mean value theorem and other exciting properties of continuous functions on closed bounded intervals. Thank you, and God bless you, and see you in section 3.4.